I repeat and apologize for some technical issues we have to start the translation. So welcome to another episode of Postgres TV, which is Postgres Open Talks. We try to repeat good talks about all the topics around Postgres to make it public accessible. So today we'll talk about new ways of scaling Postgres, and I would say new dimensions of scaling Postgres. And let me introduce our speakers for today. That's Ivan Novick and Jacque Istok from VMware now, and those people are behind the Greenplum database, which probably many of you know already. So Ivan, Jacque, you're welcome.
Thank you for that intro, and it's a pleasure to be here. As you said, my name is Jacque Istok. I actually work with our customers and our users of Greenplum out in the field worldwide, and I've been doing this this role and this job since way back in 2007 when I was working with the Greenplum startup before it was acquired and kind of got to its standing on where it is now. Ivan?
Hey guys, I'm Ivan. I'm on the product R&D side for the Greenplum technology. My journey into this started, I was doing, 2 decades back, I was doing real-time trading software. So at a hedge fund, and I wanted to kind of get more into the technology. I moved to Silicon Valley and joined Yahoo. And I joined the data warehouse team at Yahoo and started seeing how web analytics and data at huge scale worked. And then still wanted to get deeper into product development, and got a pointer by some people that I was interested in open source. I was interested in which is the best open source foundation to build a big data solution on, and found Postgres, and then started seeing, well, which companies could really build a scalable Postgres for analytics. Found Greenplum, put in my application, and I've been with the company doing Greenplum for the last 13, 14 years.
That's awesome. And thank you for going the trading world for the database world.
Yep.
I think with that, we could probably get started. I'll share my screen.
Yeah.
Yeah, sure. And I will translate you some questions as they come, or if we have some questions. So go ahead.
Absolutely.
Awesome. So I think you can all see our screen. We've titled this one Scaling Postgres because at the core of Greenplum really is the Postgres engine. And we're going to talk today about how we've leveraged that Postgres engine really to be a powerhouse for Olap and analytical and big data warehousing type activities. It is worth saying that some of the stuff that we're going to talk about today is roadmap items that we're doing with Greenplum. And so this is our required disclaimer. Some of these things may adjust over time as we continue to work on them. But we'll go ahead and get started anyway. As we've already basically said, both Ivan and I have been not only working on the Greenplum project for so many years or so many decades now, but we've also been intimately involved with both the Postgres community as well as Postgres usage with our customers. And so helping them be successful, not only on the analytical side, but also on the transactional side as they try to work through the normal day-to-day use cases that pop up across an organization. We kind of thought today that we could have a little bit of fun, and Ivan and I were talking about growing up when we made this talk, and one of the things that we loved were the old choose your own adventure books. I don't know if that translates all the way around the world, but it was a fantastic book when I was growing up to be able to have multiple stories where you would read part of the story and then choose, should the hero of the story chase the dragon, or should the hero in the story run away from the dragon? And depending on your choices, a different outcome would come up. For today, we're going to imagine. So as Ivan and I are talking throughout this conversation, let's imagine that you're part of a team and that your team is iterating on a rapidly trending, real-time new enterprise web portal that wherever you are working, that is your new role and new job, new activity that you're working on. And when I say rapidly trending, what exactly does that mean? Well, a real world example might be something like Facebook or Meta, as it's now named. If you look at the number of users in millions that was going on quarter after quarter over the last 10 plus years, you can see the number of millions of users just skyrocketed up. And so what does that mean when you're thinking about architecting and really designing how to take into account all of that scale? And so this is again kind of a real world experience for a lot of organizations today. If you were to take, kind of a high level architecture and say, all right, I'd like to build this real-time enterprise web portal, what might you do? And so if you take a look at the objectives you have here, your users are going to come in, and likely you'd have some load balancer that the users hit just up front. That load balancer would front end some number of automatically scaling web servers so that you can make sure that each of those users has a consistent web experience. Those web servers likely will have some load balancer that would go and talk to some application servers, again, within an auto-scaling group, such that each of those web servers could then function on the back end with whatever this enterprise portal is doing in order to serve up the requests from the end users. To power those app servers, you're going to need some number of databases on the back end, likely sharded in some way. And by sharded, I mean multiple copies of those databases, so that as the app servers are accessing the database, you have consistent performance for both reads and for writes as users are going through the system. One common method for being able to scale that back-end database for the app servers, for the web servers, for your end users would be using a technique called sharding. We oftentimes shard for both performance and scale. So one initial step for scaling to new heights might be taking a monolith application, right? So everyone so far has been thinking about, oh, how would I build this thing? Imagine if I had, in the olden days, a single VM. I'd probably have all of my code and all of my application server on one box, probably even, say, a database on that same box, and happily start serving it up. As I scale, I might actually start taking pieces of the database and pieces of the application and start to put it on different VMs, still trying to coordinate all of the effort in front. And so in this depiction, what you're seeing is we're taking apart that monolith that I started with so that I can scale and turning it into 32 physical databases across multiple VMs, across multiple infrastructures, and having logical shards across all of them. So again, you could imagine in this scenario where I'm depicting 3 logical shards, I might put all of the data for my enterprise application for the United States on one machine. I might put all of the data for Europe on another machine, and I might put all of the data for Asia Pacific on yet a third machine. That means my application logic needs to understand that if I'm doing something with the US, I need to route my requests to the database with the US stuff in it. Not hard to conceptualize, not necessarily hard to do, but certainly work would have to be done. And so this is, kind of the depiction between having an SMP versus an MPP, just different ways to scale. Back in the day when Ivan and I started, the most common way of scaling would be vertical scaling. Our users would call us and say, hey, my queries are going slow, my application is going slow, can you make it faster? We would then go and request more CPUs, more IO, more memory, and we would essentially build a bigger VM. Suddenly, requests were fast again, users were happy again, and everything was good. We would get more users, we'd have more data, and suddenly the system performance was slower and slower. And so again, we could go back and request a bigger VM. That works. However, there are a lot of caveats, of which we'll get to in a minute. A different way of sharding, one that was depicted earlier, would be horizontal scaling, right? So instead of getting bigger boxes, could we do something where we could have multiple smaller boxes, but have them all work in tandem? Ivan, do you want to talk about
Yep.
yeah.
Right. So now drilling into that idea of vertical scaling versus horizontal scaling. So to put a illustration for that, right? You're running a server that's from, let's say, 2020, and you've got performance problems. You look online and see, well, now I can get a bigger, faster server to replace it. And you basically, that you're vertically scaling by essentially buying more expensive, faster hardware and getting yourself out of your performance problem with your checkbook by getting a faster machine. It's easy. There's no code change, right? And you're basically, again, buying yourself out of the performance problem. And the cons to that approach are there is a limit, right? The machines, once you get the fastest machine there is, and it's still not fast enough, there's some very bespoke machines out there. They're super expensive, but essentially you've reached the limitation of how fast any one machine can go. And you really need to start looking at using more intelligence in your process and using multiple machines to do one job, right? And that's much more complicated, has application complexity when you say, well, let's just take an average machine, a commodity machine, and get 10 of them. And then can 10 of the commodity average machines be faster than one super expensive machine? And the answer is absolutely yes, right? Now, it is more difficult to operate, but that's where having a software infrastructure and a design in place to do horizontal scaling is what you need.
Absolutely.
Right. Now, when we talk about how to divide the work up, right? So let's say you're doing database work and you want to say it's not fast enough on one machine. So let's go to 10. Now you've got 10 machines. Now, how are you going to divide the work? Well, it really depends if you're doing transaction processing or analytical processing. If you're doing transaction processing, then probably what you want to do is what I would call routing. In a sense, let's say you're running a social media site and people want to update their profile. So let's divide everybody's profile into buckets. We'll put 10% of the user profiles in the database on one machine. And then when the user comes in to update their profile, we figure out which machine they're on and then run the update. That's a transaction, right? And so for online transaction processing, you divide the data evenly and then route the query to the correct database that can handle that key. Now, for Olap, that doesn't help you, because if you said, what I want to do is for that social media is I want to find out, the average time between posts, right? And I need to do a query that basically processes all the data in all of the databases, right? That would be an analytical process, in which case just routing to the correct node doesn't help. We need all of the nodes, all of the machines to cooperate to execute one query. So when the query comes in, we need to basically deconstruct that query and then figure out how to divide it into 10 even pieces of work and allocate that work to the 10 computers, have them do that in parallel, and then reassemble the final result of the query. So that would be massively parallel processing, which is exactly what you'd want for Olap.
Which, by the way, it makes me think we didn't really define what OLTP versus OLAP was. You said all the words along the way, but just for posterity.
Go ahead, you do it.
All right, so OLTP, as Ivan was defining it, is around transactions. So think of those as the online transactional processing. Tend to be a lot of queries that are very short. So to Ivan's point, I'm coming into an application and I need to update a record. That is generally an OLTP type query versus OLAP, which is more of an analytical action. So when I'm going in and trying to find an average across millions of events, I want to analyze what that average is. That might take a couple of seconds or minutes, depending on the size of my machines and the size of my data and how you operate them. Those tend to be analytical processing type queries, and hence the difference between OLTP and OLAP.
Correct. And the goal of MPP.
And actually, I have a question related to the previous remark. Basically, if we are talking about Olap in this regard, do we consider any type of Olap or some specific Olap which is good for sharding? Because, for example, just taking a look on the averages among the millions, it's one case, and then we run, I don't know, distinct on thousands of machines, it's quite different story. So is it any Olap or some specific things?
I would say 99% or almost all Olap will benefit because when essentially when you have a lot of data, right? Because when you have a lot of data, the data doesn't fit in one computer. And to process the data, whether you're doing a distinct, a count, an average, a group by, a join, all of those processing requires filtering, reading through many millions of rows, and you can divide that work across multiple computers. If you run it on one Postgres server, let's say it takes 10 minutes. But if you do the exact same job and you can divide that work to 10 servers, it takes 1 minute. Now, if you can divide it 100 ways, it takes 6 seconds. So it's the difference between the user sitting there running one query every 10 minutes versus running one query, it comes back in 6 seconds, and then they think of the new idea. What query am I going to run next? So almost,
and actually,
yeah.
And just to click into a little closer to what he asked too, if I dovetail into how you explain that, the original question was, hey, would a select distinct actually benefit from an MPP? And so if you think in your example, right, if I have a single Postgres database, and let's take indexes and caching and everything out of the mix for a moment and just say, I want to select distinct out of my table. Like, just give me a count star of the distinct items. Postgres is going to have to go through every record in order to get there. To Ivan's point, if you were to distribute that data across 10 machines, there's 1/10 of the data that each of those machines needs to actually go find a distinct record for. So each one will be able to go through 1/10 of the records. Ostensibly, that is 10x faster. And then there is actually a combination event that happens where each of those 10 result sets then go to a final stage where we get the distinct of all of those. And so to Ivan's point, 99% of the time, everything is going to benefit because we are distributing the load as wide as the number of machines and really the infrastructure that you have in order to get more things done faster.
Yeah, so it's basically it distributed aware of the specific query you run. So it can do complex things. Yeah.
Right. The first feature, if you were going to start from scratch and build an MPP Postgres, probably the first thing you would think about is, how do I update the planner to understand that that the data is not just in one machine, right? You need to, if you said select distinct, the first thing you need a query plan that knows how to break that up into X number of parts and recombine it to the letter of the law of SQL to provide the exactly correct solution and as fast as possible. And that query plan could be out of millions and billions of possible plans. You also need to find the lowest cost plan. So I think that's the first thing you need to do if you want to build an MPP is build the optimizer or planner that can understand not only what everything Postgres can understand, but also how to optimize a distributed query.
Well, and that's a great question that leads us into a little bit more of what Greenplum actually is. So Ivan, you wanna cover a little bit of this?
Right. So the idea was, when the people who created Greenplum went out to do the market study, they said, we're doing this, sharding of Postgres, this parallel processing. Do you have problems with your transaction processing? And they said, well, at the time, we don't really have problems, but we really have problems with our analytical queries. So Greenplum really became focused on the analytical queries, the MPP, this horizontal sharding. And what we did was we have the Postgres core, which knows how to do all the storage and processing and sorting and all of the operations of a traditional DB. But then we added onto it the query optimization which would be MPP, so that it would know how to do distributed queries. We also added in, you'll see in the presentation everything we added, but there's some layers there to bring extension of data out into the ecosystem, such as HDFS and whatnot. We'll get into that, but basically, Greenplum is the Postgres core with the addition to make it into massively parallel for analytics.
Yeah, and again, just to kind of say, the reason we brought up the whole sharding technique and idea is, if you were to fly over 50,000 feet and look at what Greenplum is, you might erroneously think of it as a magically sharded Postgres implementation, because Greenplum has lots of these Postgres databases that are all working in concert to solve your query, basically. And so again, we'll get into it, but this is a Postgres-based engine.
Correct, and there's a lot of solutions out there for transaction processing sharding for Postgres, where it routes to the correct node, but much less open source solutions out there that can shard Postgres and take an individual query and break it up to 100 or 1,000 parts and run all the parts in parallel.
Exactly. So tell us a little bit, or actually maybe we can bebop through a little bit of the history, because we've been here for so long. But if you think way back in the beginning, our founders had this idea back in 2003, and the idea was not necessarily a unique idea. I think what was going on back then was, if you needed to scale to massive size, the only way to do it would be to spend massive amounts of dollars with proprietary solutions such as Teradata at the time. And so there were a number of companies, Netezza being one of them, that were founded to try and figure out, is there a way we can do this quicker, faster, easier? Greenplum was one of those, and as we continued on through 2006, we were really focused on building this parallel software-based engine based upon Greenplum. In 2010, we got acquired by EMC, and EMC did actually a wonderful job of packaging that software into pre-built hardware components. That allowed for, at the time, companies who really weren't very good at infrastructure to be able to just put a box in, plug it into the power, plug it into the network, and start netting the benefit of Greenplum right away. As the ecosystem had evolved and as time went on, we continued to focus on our software side, and eventually getting to a new organization called Pivotal Software, where we shifted to a subscription software around Greenplum. And then, kind of a shock to the world, we went ahead and really doubled down on Greenplum and open sourced it. And at that point in time, the number of users of the Greenplum ecosystem spiked up very heavily. Along the way, we are the only Postgres-based massively parallel database system that has committed to getting to Postgres current. So if you look at a couple of the other ones that are out in the ecosystem, Amazon's Redshift kind of comes to mind. If you look at kind of the engine of Postgres that they're based on, this is all old Postgres, back in the 8.x days. So we took a leap. Yeah, go ahead.
To jump in, because of Postgres's liberal license, right, which essentially allows anybody in the world to use Postgres and recreate their own technology based on that freely, right? Which is why we picked Postgres. A lot of companies have taken pieces of Postgres, usually the front end, the client server protocol, and then completely cut all the core components and replaced it with their own. And I think the proprietary data warehouses out there, the ones you mentioned, have largely taken that approach. So they have no intention of providing a Postgres data warehouse. They're just basically taking some of that free code to shorten their development cycle, but then not continuing to be a Postgres-based technology. Whereas our approach, although originally was similar to them, shifted about 8 years ago and really is to provide a true Postgres-based data warehouse, right? So I think those guys you mentioned, they don't even have an intention of saying, oh, it's Postgres version X. They just happen to steal some amount of the lines of code from Postgres in 2009 or 12 and continue to have it in their product, but they're not even attempting to be Postgres-based data warehouses, I think.
Absolutely. And I don't want to, focus on the history. Let's focus on the current and the future, right? So Greenplum 6 is out today. We've up-leveled to Postgres 9.x. Greenplum 7's beta is going to be coming out, later this year, and that'll be up-leveled to Postgres 12. Why it's important is because both the queries, the ecosystem, and a lot of the analytics and machine learning that you can do in Greenplum can then easily be shifted back to Postgres for your transactional processing, which kind of gives you this open source powerhouse of both transactional and analytical capabilities. So let's learn a little bit about the architecture, Ivan.
Okay. So essentially, you've got one Postgres at the front, which is called the master node, and then from there, you've got X number of, let's call them hosts. We can call them segment hosts or worker hosts. And on those hosts, we actually run usually more than one Postgres. And the reason is that although there are advances being made in Postgres's parallelism, because it's largely built for Oltp, it still doesn't leverage the full power of a single host completely. And so we actually run, let's say on average, like 8 Postgreses on one host. And then we'll take that and extend it and say, okay, let's get 4 hosts, 10 hosts, 40 hosts, 100 hosts, each running 8 or 10 Postgreses, and create a system altogether that might have 100 or 1,000 Postgreses all connected through an interconnect, which is a commodity Ethernet interconnect over software protocols, and essentially then allow the queries to come into the master host, query planning, and the data divided up into the worker hosts and all the processing done on the worker hosts. And really the master host is very light. It doesn't use a lot of load. It just quickly divides the query up into pieces and sends back the results.
So I just want to double click one thing you said. We run multiple Postgres on a single host. So does that mean that Greenplum can actually be parallel on a single host?
Yes. So you can run X number of Postgres segments on one host, and it will be meaningfully faster because of the extra parallelism we will create. So there are in the latest Postgres, there are certain parallel features and certain parallel query execution nodes, but it's not fully parallel, right? So on a host, we can do a lot more parallelism, and we do that, right? So we can
and what the one thing I want to just interject there. When you say it's not fully parallel, what you really mean is that it's not fully massively parallel shared nothing, which I think is actually super important.
Right. So if we want to see, let's say, get a modern commodity server that has 50 cores and 24 disk drives, and we want to run a typical, let's say, select all the data and do an aggregation group by result, right? We're going to divide that into 10 parallel workers, start churning through, each worker reading off of 2 SSDs, and 10 of those guys going in parallel. It's going to come out to be 10 times faster than running it in a single Postgres on a single host. That's all within one host. Then we're going to say, okay, now let's have X number of hosts.
That's awesome. Okay, so where can you actually run Greenplum?
May I ask a question? How do you manage memory if you have 8 Postgres servers on one virtual machine? What about the size of the the buffer pool, shared buffers value, and so on? How do you manage it?
Well, we know how much memory is in the total, and so we'll set it accordingly. Maybe to reach, let's say we have a terabyte of memory, we might then say, okay, so that's 100 gigabytes for each Postgres, and then maybe 25% of that will allocate for shared buffer. So it's just configured at startup time based on how much memory you have and how many Postgres is at a reasonable figure. So that's
it is also worth noting that we depend a lot on the OS sometimes to do a bunch of caching on our behalf, because analytical queries tend to consume a lot more data, and so they fill the cache quite quickly. And so the cache for an Olap query, sometimes you could argue, matters less than the cache for a transactional query.
right. So if you go back to the roots of the Postgres design and architecture, right, and if you compare Postgres, let's say, to Oracle DB, Oracle DB doesn't run generally on a file system. It will generally be given direct access to the disk device, and it will do everything. But the whole approach and philosophy of Postgres was to not reinvent that wheel and to use the operating system and use the file system to do that job. And the idea is that you could write millions of lines of code doing that job, and you're going to get some, modest performance gain, right? And be much less portable. So the whole Postgres design is to say, we don't do direct IO, right? We let the operating system do its job and the file system do its job. And the operating system, Jacque, to your point, it has a cache. So you can allocate, 500 gigs to OS cache, right? And then as you're reading data, that'll help the IO of the, if you run the same query twice in a row, the second time it won't go to the disks.
Correct, because it's already in the Linux cache, for example.
Right.
Right, but this Linux cache is less smart in terms of database specifics. For example, if you create an index, there is a buffering that can be used if we rely on the buffer pool. But in the page cache, it will occupy a lot of space in memory, right?
Right. And so if you look at two basic use cases, one is a very typical Olap query, like a select every product sold at Safeway stores in all the and give me the count of each product category, how many things were sold, right? That's a group by query. That's going to be a very consistent read. So you're going to be reading and processing, and really the cache becomes a lot, I would say, less relevant, because what's the most important thing is the speed of the devices and the speed of the CPU, because you just keep going through more new data. You can't cache it all, right? And so for that kind of a use case, we don't see this part being important too much. And then also, now let's say that you wanted to find a specific sale. You had like, hey, someone went to that Safeway store and we have the transaction ID if they bought a Coke, and you want to find it in an index. Well, in an Olap system, if you can get an index query to return in 50 milliseconds, and with a little more tuning, you could have got it in 20 milliseconds. Generally, people are satisfied with 50 milliseconds versus 20 milliseconds. In an Olap system, it's not as sensitive to the speed of the index queries. You already have the index; it's going to be super fast compared to a scan. And many Olap products like Snowflake, Redshift, et cetera, don't even support indexes, B-tree indexes, right? So you're already way ahead of the game there. So though some of those tunings are less relevant in the Olap use case.
One thing you said earlier, Ivan, was around the portability of Postgres itself. So from a deployment aspect, let's talk about Greenplum.
Correct. So there's two historical approaches to building database products. One is to pick one infrastructure, whether it be a very curated hardware device, and say, our database literally will only run on our hardware, and to kind of make every component work perfectly there. That's called an appliance. There are database appliances out there, and they have moderate success in that way. You could also do the same thing, for example, in the cloud. You could say, we're literally building our system to only run in Amazon, right? And you could cut all of the genericness of the code and say, if you want it that way. The other approach, which is what we do, is this is portable standard-based software. So you say, if we're building standard-based software, where are the standards, right? Our software runs in Linux environments, running on POSIX file systems over TCP/IP Ethernet, right? And we're building that very generic infrastructure, that very generic database technology for ourselves and for the world to consume in any of these environments, whether it be environments in the public cloud, environments in bare metal, environments in virtual machines, right? We're saying that we're creating the software stack based on these open standards and not taking shortcuts to tie it to a specific thing. And we think this is the long-term best gift to the world, as opposed to just saying, well, we're going to make it super easy on exactly this hardware and we're going to charge a high price, or exactly on this cloud and charge a high price and make it proprietary. We're making it open source, open standards, and portable to all mainstream environments.
Right. And truly, as VMware would call it, truly hybrid cloud. No matter where you need to deploy, no matter where your data is, you can run the same queries, the same engine. So, with the Greenplum 6 introduction and the up-leveling of Postgres, I believe we've truly gotten to a spot where we're HTAP, hybrid transactional and analytical processing. What does that mean, Ivan? Right.
So when Greenplum first started, it was a good enough accomplishment just to solve these basic Olap queries, these TPCH group by aggregate types of queries, right? And we deployed it to hundreds of customers around the world, and the customers came back and said, hey, it's really good. We're really getting great performance on the Olap, but now that we got the data there, we also have end users that want to do lookups, and we don't want to copy all the data to another database. What they told us is that you solve the main thing, but the main thing is not enough. You need to have to be a data warehouse that meets customers' requirements. You need to be more mixed workload. You need to be more HTAP. You need to support more complex environments, right? And what does that mean? Means that concurrency needs to be high, right? It's not good enough to say this works with 20 users, right? It needs to work with thousands of users. It's not good enough to say everything is a scan and we don't support indexes. You need to support indexes, right? It's not good enough to say single row inserts are not going to be ideal, batch everything up. And it's not good enough to say don't do updates and deletes. You need to do what a database can do, right? And do it as well in combination with your Olap. And you need to layer on that workload management, right? So workload management is well defined in the data warehousing space over the last 30 years. Probably it started with the mainframes in terms of how do they schedule jobs on the mainframe. But when you go into 1,000-person environment running millions of queries, there needs to be a software module to control how and when workloads come into the system and how they're prioritized once they're in the system. So all of these things were essentially added in Greenplum 6 in 2019, whereas the original Greenplum was really just your pure Olap engine, right? So now you can create complex rules to manage the performance and the allocation of resources within the engine, which is a value add on top of Postgres. Now you don't sacrifice Postgres's high concurrency and index lookups. These come along and are supported in Greenplum and the updates and deletes. So similar performance that you would get from single node Postgres, you would also get that performance from a Greenplum environment. Now it doesn't, so basically you can blend together the ability to do lookups, updates, deletes in the same environment without having to create a net new environment to answer certain questions.
Awesome. So we have talked about this before, this idea of shared nothing, and it's really all around distribution of data between and amongst all of the Postgres databases that are in the Greenplum cluster. But can you describe this picture for us, or do you want me to do it?
Right. So this is now we're getting into the implementation of how to divide data across, let's say here, 24 Postgreses, right? And the way you do it is, and the way you don't want to do it is to have, the way we do it is based on keys, hashing and keys, right? So when you have a table, the table has certain columns, which are the key. And then based on the hash of that key, it algorithmically determines which Postgres that data belongs to, which is very important when compared to Hadoop, where there's a concept of a metadata server. So like where you basically figure out at runtime where to store data and store that in yet another database. And then anytime you want to get data, you would need to look it up in a database. Where is it? There's just the data itself determines where it lives based on its signature of the data, which is a very low overhead way to find and store the data distributed in a system. So in this case, you've got an order table, and we've designated the order ID, which is pretty random, to be the distribution key, which means that depending on what order ID your order has, will determine which Postgres it's in.
So me as a DBA or me as a developer, when I create the order table inside of Greenplum, do I have to do anything, special?
Yes. So, there are default settings that you can do quickly, and then there are optimizations once what you would do is, let's say you have 50,000 tables. I would tend to use default settings for all the tables. And then I would go back and say, what are my 10 biggest tables? And for the 10 biggest tables, I would go and change all the settings, right? Because decisions of how things work when your table is huge will have huge performance impacts, right? So let's say, again, you've got a million tables and a lot of them are mediocre size. Just we'll create them as just default randomly distributed. But then I've got let's say, again, I'm sorry, Safeway, I hope I have permission to use your name. Let's say I'm working at Safeway stores and I want to create a table that says sales. And I want to store one row for every sale at every Safeway store. That's going to be a huge table, right? And for that table, I'll probably say, let me figure out which column in that table would make sense to use to make an efficient distribution key, right? So you go back through your biggest tables and kind of tune the parameters to give you better performance.
Sure. And just to say it out loud, because you didn't say it, but you implied it, I want to minimize the amount of movement of data as much as possible so that a single Postgres in my cluster can do as much work as possible so that we don't have to distribute that data, or as you said in Hadoop, that's called shuffling. And so if I could align the sales of a store with the dimensional aspects of that store such that joins can happen locally within Postgres, I won't have to shuffle data around to where all the joins can naturally take place. And so that is the optimization that you're talking about. But for everybody in the audience, recognize that Ivan said there are defaults. And so you will still have, in this case, 24x workers working on your data, working on your queries, because it is still massively parallel, and you'll still get those initial benefits. Now, if we keep kind of going, Postgres has a notion of kind of partitioning within a single table, so that you can have almost an implied index of sorts, right? If you partition by date and you specify date in the filter, you don't have to go through all the partitions in the table. You can go straight to a specific partition, almost as if it was indexed. We have that similar concept, right, Ivan?
Right. So vertical partitioning, which has been available in Greenplum since the beginning, also been available in Postgres for the last few years, right? The use case for this type of partitioning, right, is that usually it's done on time-based data. And so again, using the Safeway example, a lot of times, let's say I want to store the sales for the last 10 years in the database, but I only want to analyze the sales from the last 1 year. So by partitioning, you're basically creating separate files in the file system that can be completely ignored when you execute the query, if the query planner realizes that the query is limited to a certain subset of the data. So again, if you have 10 years of sales data and you say, give me the average sale price for the last 1 year, then the IO, the reading of the data, will only be for the last year. We will not read, scan, filter, or process the next 9 years worth of data. So if you don't use that feature for this query, you will be literally 10 times slower, right? And so you could have 50, 100 partitions, and that could provide 50 to 100 times speed improvement for your workload. And it's really important when the data is big, like when you want to store every sale at a major retail chain forever.
Right. But now we took partitioning to what I'd almost call like an extra level. You want to talk about polymorphic storage?
Right. So in Postgres, there's one storage type, namely what we call it heap, and it's the storage type for the data. Now, that will be the default storage type in Greenplum. But then when you go back and say, hey, let's take a look again at our 10 biggest tables and see if we can't make this perform better, we provide a couple of other knobs to accelerate your workload. So the first knob we provide is a compressed table option, right? So you can pick a compressed table and then essentially use compression to store the data in much smaller footprint. So this one probably is best illustrated at a stock exchange. So let's say we're storing all the trades on the New York Stock Exchange forever, and we want to have, there's a lot of repetition in the trades data, right? Like you've got the symbol, you've got different things that repeat. And so compressing that data, our customers see 4 to 40 times compression, which when you have a petabyte of data and it becomes, 25 terabytes, you've dramatically changed the cost equation in your hardware, right? So it's absolutely critical to enable compression in the data when you're talking about big data. Otherwise, you're throwing millions of dollars into the ocean, right? So we support the compression option. And then we also support another tweak, which is the storage to be either stored in rows or columns. So if you come back and say, hey, it was the every trade at the New York Stock Exchange forever, well, if one trade is the ticker symbol, and a lot of the trades are Microsoft, MSFT, and there's a million trades at Microsoft, the compression algorithm can suck that down to be like, 10 bytes, right? So, when you store columnar versus row-based, there are certain advantages that, again, manifest when your data is huge. So we've got the compression, we've got the column orientation, and the third one is, I don't even want the data stored in the database. I want it stored externally, let's say in S3 or HDFS, right? And then I want to just completely offload the storage to a low-tiered storage in an open format like CSV or Parquet, Avro, ORC, right? And so that's yet a third tweak to say how to lower the costs of a big data solution.
It's actually very interesting. It sounds like you have basically all the good things from all the words. So basically row-oriented, column-oriented, and you even can store it on S3. But basically, to put the data in such a table, it sounds like very, very, very difficult to keep all those features which are good for reading data. Do you have some I don't know, optimization how to load the data in such tables, or maybe you will cover it later?
Yeah, well, in essence, where I'll go with that is that from the end user, they load the data and query the data from this parent table. So they load and query sales. So you say insert into sales, select from sales, and the DBA sets up the structure as an optimization, but the end user doesn't interact with this structure. They just say insert into sales. And then when the rows come in, they get routed correctly. So they don't need to change their code when they load. So if I create a S3, let's say we're doing sales for the last 10 years, and I say all of these years are stored in S3, you just load to the sales table, and then Greenplum will move the data to S3 without you doing anything. Right? You just set up the link saying,
So
here's
it's
the
basically a sort of automatic retention workflow or something like this, in a way.
Let's start with the more technical point, right? So in the query plan, you have these operator nodes, right? And there's an operator node called like a read or a scan operator, and they're writing operators, right? So we have another operator, which is an external reader and an external writer. So you'll look at the query plan, and the query plan, if it's writing on top of such a table, let's say it's reading from this thing, right? The query plan will say select from, at the bottom of the plan, it'll say external table scan from S3. And when it gets to that part of the query plan, it'll just start doing S3 protocol, right? So from a query execution point of view, it's just integrated into the query plan as a node, which says external scan or external write. And those are just read and write, right? Now, so basically you create the schema, and then once the schema is created, if you do alter table, or if you do select from one table, insert into another, create table as these kinds of things, you can completely transfer everything from one structure to another using SQL that you don't use where you're not looking at the storage layer.
And we always say, kind of summary succinct of this one is that we have the ability to do all different types of storage. Depending on your use case, you'll see folks deploy different techniques. Ivan kind of implied it, but the most easiest for everyone to understand is just the typical row-oriented, very Postgres-oriented kind of tables. Yeah. As we continue to kind of exist over time, we start to make optimizations, and oftentimes column-oriented provides a lot of that storage compression that we can get while still, again, for certain use cases, picking up off of disk 1,000 column, table means that we're picking up 1,000 columns off of disk. That's a lot of I/O if you're only looking for 2 columns. So column-oriented can actually provide a lot of optimizations in general. And then what we usually find in a lot of customers is that the most recent data is queried 85% of the time. Then after that, there's a next recent, which is queried, another 10% of the time. And then there's like the old data that needs to be kind of near online, but can be on the slowest and the cheapest storage possible, hence the year 1, year 2. But from an end user standpoint, all of this is just within the sales table and is completely, agnostic to them, where the DBAs are trading partitions along the way to optimize that ultimate storage. And then, we talked about compression. There are different compression techniques that actually can provide different value to a customer. You want to talk about any of this, Ivan?
Yeah, I mean, so the compression is an option. So when you say create table, there are flags that we introduced in the syntax to the normal syntax of Postgres that'll say create table, same syntax, but then you say you can add with compression or with storage options, right? And we studied all of the open source compression algorithms to determine which would provide the highest performance and best rate of compressions, and found and invested into an algorithm built at Facebook called Z Standard, which is we think, the world-leading open source compression algorithm. And that's integrated into Greenplum, that the user doesn't need to do anything other than choose to use it. And the data will be stored in that compressed format and give you that huge reduction in cost of storage.
Right. And the reason you'll see these different compression types, right, is some use more CPU, some use less, some use or get better compression, some use less. So your mileage may vary depending upon which ones, but they're all available. If I sort of get off of storage for a second and kind of think, one of the taglines we've always talked about for Greenplum is Greenplum is not just a database. Despite the Greenplum database nomiker, Greenplum's not really just a database. One of the things that we can do is actually extend it because of Postgres and because of its object-oriented relational database, kind of stature. One other thing that we have is this ability to create data types that aren't your traditional kind of data storage. You want to go through any of this, Ivan?
Yeah. So most of this is not unique to Greenplum when it comes to Postgres, but is unique to data warehousing when you look at proprietary competitors, right? So many proprietary competitors don't have as rich of an extension ecosystem as Postgres. Postgres has probably the most robust set of both data type and also functional extensions to the database that come from the worldwide community of developers, right? So there is JSON, XML for semi-structured data. There's text specific search and indexing data types. There are use cases and techniques to store image and video data and do analytics and reporting on video and image data in Greenplum, as well as network IP addresses, network security logs, sensor data, geography data through PostGIS, which is a huge use case, and as well, something we did add on the Greenplum side that was native beyond Postgres, which is graph analytics. So the ability to do things like PageRank algorithms and whatnot in the database.
Awesome. So I think this next slide probably should have been when we were talking about storage, but I'll just quickly say that between the distribution of data and the partitioning of data and the massively parallel shared nothing nature of Greenplum, I think this is a nice visual representation. When you're doing a count from that orders table for a specific date range, you can see that without partitions, when we do that count, typically each of these 12 Postgres databases are going to count their orders for their date and then give you an answer. When we add partitions into the mix, we still have 12 Postgres engines counting the orders data, but because it's in a separate partition, they're only reading, in this case, a 1/6 or 7th of all of the data. And again, kind of taking out the fact that we could also index this as well, but because it's partitioned, it's an implied index. And so you're not bearing the cost of updating that index as you're loading the data. And by the way, as we had said before, with the polymorphic aspect of this, some of these partitions could be columnar, some could be row, some could be compressed, some could actually exist on S3 or HDFS.
So, and Jacque, if you go back for a sec, right? When a customer has a problem and they say, we're running our business intelligence report, it takes 24 hours. I want it to run in 5 minutes. How do we make that possible, right? Well, if you have 100 Postgres segments and each Postgres segment has 100 partitions, you're quite literally making the work 10,000 times faster, right? So by just going from a naive approach of saying, here's one Postgres, not partition, to saying, here's partition and sharded Postgres, right? Both 100 ways. You literally take a query that takes 100,000 minutes and it runs in 1 minute.
Yeah, it's honestly, when we show this to customers, it's literally jaw-dropping.
Which is just exactly what you need for that problem. Yeah.
Absolutely. Now, one other kind of thing you had talked about before was there are optimizations that can be made with regards to distribution. So by default, we'll try and kind of equally distribute data across all of these Postgres instances or segments. But there's drawbacks when you start doing heavy joins because data has to shuffle around. One thing we introduced was the ability to make the shuffling a little bit easier. Can you talk about this one, Ivan?
Right. So this is another tweak or optimization. So let's say, let's backtrack and put in some terms, right? So in data warehousing, there's a concept. Shoot, I just lost the name of the concept. The fact and dimension concept.
Yeah.
So basically,
a snowflake model or a star schema.
Yeah, star schema. So basically, think of a typical your business here, right? You know, the sales table is going to be huge because again, if we're that supermarket store, we're selling billions of items. I mean, not billions of items, billions of individual sales. But the actual list or table of stores is only going to be like 1,000 stores, and these things are called dimensions. The facts are the individual data points that are generated millions of times per day. The dimensions are your fixed business elements, like the number of stores, the employees. This information doesn't churn as fast as the actual sales. So frequently what happens is you have all these related tables. You've got one big table or three big tables in the middle, and then a bunch of smaller tables, which are dimensions around it, which you want to join them all together to produce a result. So what we enable is another distribution option where you can actually replicate automatically all these small tables to every Postgres, so that the fact table is distributed to is distributed or cut into pieces, but the small tables are replicated into every Postgres. So when you go and do the join of these 5 tables, it's literally done locally in every Postgres. We don't need to shuffle these 4 tables or 10 tables all over the network. It's all done locally. So it's fully parallel computation.
Awesome. So then, if we continue the differentiators between Greenplum and Postgres, or really in some ways between Oltp versus Olap, one of the things that we recognized about a decade ago, I think, Ivan, was that we really needed an optimizer that wasn't just really good at transactions, but really understood big data. So can you talk a little bit about Orca?
Yeah. So Greenplum has 2 options when it comes to the optimizer. We have the standard Postgres optimizer, which is called the planner. And we also have the Greenplum Orca optimizer. And both of them take input and provide output. The input is essentially the SQL, and the output is essentially the query plan. So these are done on the master node and are highly algorithmic calculations to search the infinite space of possible ways to solve the translation of SQL into physical query execution. And Orca was designed as kind of based on the latest academic literature to do a ground up query optimization for distributed systems, and then plugs neatly into and intercepts the SQLs, and then generates a distributed query plan. And it has the capability to handle some of the sweet spots, which are really hard to handle in the original planner, things like correlation. So when you talk about correlated subqueries, common table expressions, being able to parse through the views, through the common table expressions, and to optimize all the pieces. The Orca optimizer is our default, and it's running millions and billions of SQLs and doing a great job.
Awesome. So a lot of the demonstrations or examples that we've given so far talk about how we can leverage the underlying infrastructure, we can avoid the use of indices. But as you said earlier, having indices actually is quite a boon for certain workloads. But it's not just one type of index, right? It's a bunch of different kinds depending on the use case.
Right. So this is a key differentiator in the data warehousing world. So very frankly speaking, when you look at the new generation, when a new data warehouse is created, and I would call most of the cloud-based data warehouses relatively new, right? And most of the cloud-based data warehouses in general, right? They don't support these use cases, right? The use case here is that in your data warehouse, you also need index lookups or fast drill through queries. And that we know from our business experience is a real world customer use case, is that you can't just tell people to scan when they want to do certain things. They want to find that row right away, right? They want to do millisecond latency on the data warehouse. So because we are in Postgres technology, the only thing we needed to do was to make our optimizer smart enough to determine when it's better to do scanning and when it's better to do index lookup. But all of the index technology is already for free in Greenplum from Postgres. And Postgres actually has multiple indexes for geospatial data, text data, B-tree data, right? And so all of these indexes are available in Greenplum, and the optimizer knows based on the SQL when to put it in the query plan and when to not put it in the query plan. And that makes for the multimodal or mixed workload where you can be combining lookups, updates, deletes with your big scan queries in the same database, which is a fairly unique feature in, I would say less than 5 database technologies in the world can combine indexes, well-performing indexes with big data scanning.
Awesome. So now I know we're hopefully in a good state for time. I know we started a little bit late, but let's keep going here. Early on in my career as a data consultant, disk quotas were something that I rapidly, kind of burned through with reckless abandon a lot of times, always constantly asking DBAs for either more spool space or more areas for me to play. When you get into an environment that's got millions and trillions of datas, oftentimes that can take a toll on the infrastructure. So one of the things that we have, right, is the ability to control users, or at least give them some subset of space. You want to talk about that?
Right. So again, this didn't come free from Postgres because it wasn't as relevant in a Postgres context, right? So we had to build a overlay layer into Greenplum that could enforce these limitations in a high performant way, so that if you have a data scientist comes on the system, maybe it's their first day in the job, and they go to the biggest table in the system and they say, select star from huge table and insert into my new copy. And what they've just executed in 100 in the size of a tweet is a job that essentially is going to now store another copy of, let's say, $1 million worth of hardware, right? And the company wants to reject that. So we just couldn't survive without enabling disk quotas to have a multi-purpose system and allow people to come in and do things without having the right safeguards, right? So disk quotas is one of the workload manager functions that needs to be there once you start dealing with big data.
Totally. And speaking of when I was doing consulting, I would always have said one of Greenplum's most amazing strengths is its ability to do bulk data loading, because I've never seen anything as fast.
Right. And the trick to bulk data loading is really parallelism, right? If you have 20 machines and those machines all have their own NICs, network cards, and they all have dedicated storage, shared nothing storage, right? The trick is, how do you load and keep all of the nodes operating at full speed and not basically bottlenecking through a central point, right? So the bulk load in Greenplum will initiate the connection using ACID and SQL, but then essentially under the hood directly push all the data to the worker nodes and avoid any bottlenecks. And this can achieve, depending on how many nodes you have, it's going to be faster in a scalable fashion, right? So 20 nodes of data loading will be 2 times faster than 10 nodes. And you're talking about terabytes per hour of data loading per node.
Right. And literally, I have never seen Greenplum be the bottleneck for loading. It's literally always the source of where data is coming from. The physical I/O of those, in this particular picture, of those ETL nodes, they serve it up, and Greenplum scoops it in as quickly as the network and the I/O can take it. And then we took it to one extra next level with streaming data directly into Greenplum. Do you want to talk a little bit about that?
So again, so the bulk loading feature was there early on, 10, 15 years ago for us. But about 5 years ago, customers, like these huge internet companies and others said, the traditional model of ETL is a daily data load, right? And so companies operating with big data would frequently have a daily job that would load all of yesterday's data. Then people would run reports. And about maybe 5 to 8 years ago, people in general said, that's not going to meet our business need. We need to move to real time, right? So the old model of daily load and then reporting was just not agile enough. And to support that, technologies like Apache Kafka came out. So Apache Kafka is now, capturing all of the data. And what we've done is we've created a ingestion component that can essentially listen to a message bus like Apache Kafka, and nearly in real time, near real time, pull in an efficient manner all new data from a stream, whether it be Kafka or RabbitMQ streams, and continually load it into Greenplum. And not only that, can guarantee automatically once only delivery of every data point, and resumability. So if the streaming goes down, the data is still in Kafka, you can reconcile what was the last data inserted, pick up from the last point, and kind of atomically guarantee every single record loaded exactly once in high speed and in real time. So that's like, where the world goes, data loading.
So it sounds like you're saying that if I created a topic in Kafka, Greenplum would just attach to that topic and load everything I threw into it.
Right. It's like you put two magnets together, they connect, right? And now they're transmitting the information. The data is being transmitted automatically from the Kafka topic into the Greenplum table that you've mapped.
So basically, it's you map a single table, or it's more like, I don't know, logical replication. You can split the information in different structure in Greenplum.
So there is flexibility in terms of how to program it. But starting with the very simple use case, you would map one topic to one database table. Mm-hmm. So let's say, for example, you had a topic called
orders.
Orders on my website, right? Or whatever it is. But it's generating data for that, big event stream. Then that would get loaded into an order table. So you'd have, and you can do a lot of those transformations beforehand in Kafka. So you can kind of have one Kafka stream generate another modified Kafka stream, right? And then essentially there's many programmatic ways to kind of modify the data as it flows in Kafka, new Kafka queues, and then as it comes into the DB. But finally, you need to load data into tables, right? So you need to pick which source goes to which table.
Now, we've talked about how fast it is to load. We've talked about how you could stream data in, but I recognize that not all the data that I'm querying is probably going to be inside of Greenplum. So how do I attack that?
Right, and this is very similar to if you're familiar with foreign data wrappers and Postgres, right? The idea is that, and I just talked to a customer doing something like this recently, but you've got your operational database, your operational data warehouse where you're running millions of reports, but you might also have another layer that has, cheap and deep storage, archive data, historical data, image data, flat file data, data that's part of a data lake, open source, open format data, Parquet data, right? And you can essentially create reference tables in Greenplum that essentially point at data that's living outside of the database, and then use the query engine of Greenplum to query it. The only difference will be that the fetching of the data won't be fetching from the native Greenplum storage. When you run the query, it'll be fetching remotely from another source. So very simplistically, let's say you had data in Oracle and you said, I want to create a reference table, right? You can say, I've got an order table, but really the data is in Oracle. And I want to join it with my HR data, and my HR data is in Hadoop. And so I want to say, select Greenplum, the order table and the HR table. One of them is coming from Hadoop, one of them is coming from Oracle, and join it with a third table, which is stored locally. The whole query engine will work seamlessly. Just the fetching of the data can be pointed referentially to these external sources, whether they're S3, Hadoop, Oracle, and these open formats. And that allows to kind of create this data federation lake to kind of embrace the ecosystem, not just like creating a silo.
Right. It's almost including Presto-like capabilities within Greenplum so that you can do exploration. And then once that exploration bears fruit, you can start to optimize by pulling some of that data in locally and doing local joins and whatnot. But
Sure.
this allows for that natural, need for data within and data outside.
Right. It's sometimes called data virtualization, data federation, right? You're trying to point your system at Greenplum and query it without knowing truly where all the data is, and then having Greenplum be smart enough to say, well, what workloads can you push down to the source system? Can you do filtering at the Oracle layer before it comes back to Greenplum? Can you do filtering at the Hadoop layer, right? How can you make the entire thing as efficient as possible?
Perfect. And actually leads to the next slide around, kind of integrations in with other technologies. I think that Spark is used pretty heavily in a lot of customers today for a lot of reasons, and we have an inherent connector or capability here.
Right. So Greenplum, again, trying to avoid the data silos. So the companies and users want to have ecosystems, not silos, where everything can be accessed by all the different tools. One of the key tools used by data scientists in today is Apache Spark. Apache Spark is popular and powerful and provides machine learning and certain types of use cases that data scientists gravitate to. Now, in order to access Apache Spark, that they might think, well, we should move all the data to HDFS. But if that same data is being used by SQL and by Greenplum in all kinds of business processes, what we enable is that you can just point your Apache Spark at Greenplum. Greenplum just becomes a different data source. So the same way you could run Apache Spark and reference, here's my data, it's on, when you open the Spark connection, it's coming from this HDFS. This is just a different data source. And under the hood, we have the code, the driver code that makes very efficient parallel accesses to Greenplum from within the Spark driver, so that the data scientist doesn't know the difference, whether they're reading from HDFS or Greenplum, but you don't need to have the data in HDFS. They can directly just suck the data from Greenplum without even knowing anything about SQL or Greenplum. They just run Spark and read and write data with the final destination being the database.
Right, and which has actually been something of interest to a lot of our Spark users, where they can get the full capabilities of a relational database engine like Greenplum, and kind of, ignore or without needing
without putting it in a silo. You're not siloing it, saying once it's in Greenplum, you can only query it through Greenplum. You can also query it through Spark.
Correct. Now, Spark is one way of doing machine learning and analytics, but we also have our own built-in way that scales, as much as your data, right?
So, okay. So what this slide refers to here is, again, something that's derived entirely from Postgres, which are user-defined functions. And user-defined functions and user-defined languages. So Postgres and Greenplum, by extension, have the ability to embed programmatic procedural languages and use them from within the context of a SQL query. So you can use Python, Perl, Java, R to process data in line when running Greenplum analytics. So as an example, if you had some text data, let's say you had tweets, right? You were storing all the tweets about things related to your company, and you wanted to analyze the sentiment of people. Well, Python already comes with great sentiment analysis libraries, right? You don't need to reinvent that wheel. So you could just say, select all tweets where the sentiment has a negativity score greater than 99. And then essentially write a function that processes each tweet row by row using Python and LTK, returns a sentiment score, and now it becomes a query, right? You've said select all tweets, right? And you can also say join it relationally with other things. You can say where, the IP address is within this range, and use SQL to filter it down or to join it with other data sets. So really
And
bringing
the real magic there, right, is that you just took that Python, model, and you've parallelized it, because we've got in a lot of these examples 24 different Postgreses running, or 50 or 100. So now or 1,000. Now you've automatically parallelized it.
Right. So you can 1,000-way process the tweets or whatever you're processing with Python code or with Java code, right? And it's going to be 1,000 times faster than doing it in line. And you can then filter and join it using traditional SQL without getting out of your SQL kind of environment.
Absolutely. So everything we talked about so far is like just, barely scratching the surface of all the capabilities of Greenplum. Having said that, we wanted to, at least talk a little bit about what's new and what's coming new for between now and kind of the end of the year.
Right.
Again, let's not forget about the disclaimer that we talked about when we first started. But let's start with the first one, number 5.
Right.
Yeah, it's supposed to be like a huge leap since 9.4 to 12. It's like many fans expecting that.
Right. So let's talk about now the roadmap of Greenplum. And as Jacque said, everything future looking may change, right? And if you buy the product, you should buy it based on the features we have today. That being said, the top 5 features coming out in just before the end of this year that we're planning to do. Number 5 is the PG Bouncer connection pooler. We've added LDAP integration. So PG Bouncer allows for bigger groups of users to pool their connections, right? And to save resources, really supporting large environments. But these large corporate environments also need security. So we need to integrate, and we're going to be releasing the LDAP integration with PG Bouncer so that you can not only do this connection pooling, but also have it sync and authenticate through LDAP. Number 4, we have had Kafka streaming integration for that real-time data ingestion. Now we're going to support RabbitMQ as another source of streaming data. Number 3 is a Python interface to Greenplum. So Python data scientists, the reason they like Spark is they like the data frame approach. They like to code in Python. They may not want to revert to a SQL environment. So we're going to be providing a Postgres compatible and Greenplum compatible Python data science client library. So you can go in there and say, link this, give me a data set from the database, but then essentially start creating data frames and doing data frame operations just like you would with Pandas or with Spark. But really under the hood, that generates SQL that you don't need to know that will go and execute that work on the database side. So we're really trying to open up the power of the data and its processing power to data scientists that prefer to work in data frames and in Python. Number 2 is, as we showed, we have this parallel set of Postgreses in a database. When we do backup and restore of the system, it needs to do all of those atomically together, and it makes it quite tricky historically for us to then restore if somebody changed their topology in between. So we're creating another layer in the middle to allow you to say, okay, we're going to back up from 50 Postgreses, but restore to 33 or some random number like that, right? Because it allows you to migrate to different systems and different topologies, and that's highly requested capability. And number 1 is a disaster recovery solution. So Greenplum being based on write-ahead logging, right? The customers are really looking for a way to do DR using the write-ahead logging. And so we've had to do a couple of minor injections into the system to make it MPP friendly, but we'll be supporting the same Postgres write-ahead log archiving features on an MPP basis to really help with the disaster recovery use cases in Greenplum. There are other solutions now, but this will be more exciting.
Now, and it's funny too, Ilya, you just literally talked about the improvements between the different versions of Postgres. Sometimes I don't like to get hung up here on what version of Postgres, kind of matters or not, because if you look at all of these solutions that are Postgres based, they all have great capabilities with whatever version of Postgres they're on today. There's a lot of greatness for the fact that we're actually continuing on our journey to be with Postgres current. But Ivan, you want to talk about that journey that we've been on?
Yes. I mean, the backstory was we took a huge leap in the very beginning creating this MPP technology by using the Postgres code. So the 2006 Postgres code is where we started. It took us roughly a decade to build that technology. Once it was locked in, we started the journey. You can see somewhere here between Greenplum 4 and Greenplum 5 to say that, okay, now that we have the core MPP technology solid, we really need to start reintegrating all the new versions, right? And so there was a lot of groundwork and cleanup work in Greenplum 5, and that left us still at a 9-year deficit to Postgres. In 2019, we released Greenplum 6. That included 6 versions of Postgres integrated into it and all MPP friendly, right? So 8.3 or 8.4, 8.5, 9.0, 1, 2, 3, and 4, which is essentially something like 5 years worth of Postgres development. It's now our premier version. It's based off of Postgres 2014, but it's our premier production version. And if you go to Greenplum GitHub and look at the open source, you'll see it's now based on Postgres 12. That'll be enterprise GA'd in 2023. And that's the Postgres as of 2019. And for me, 2019 starts to feel like a fairly recent version. Going from there, personally, my goal would be to have something like a 2-year latency because it allows the features to mature and bake and for us to integrate MPP technology into it. But really looking forward to see Greenplum 7 based on Postgres 12. And I'm not sure if you have the slides about what all that contains from Postgres features point of view after this one.
I do not.
But there's a tremendous amount of features, as Nikolai was saying, like Brin indexes and JIT, just-in-time query compilation. That one alone, like, hey, I've got a 1-hour query. Well, now I turned on just-in-time compilation, it became 30 minutes. Bang, like that's magic, right? So, and I know a lot of hard engineering work went into creating that, and we can leverage that in Greenplum. So Postgres 12 will be awesome, and Greenplum 7 will be awesome.
Absolutely. So now, just the last 1 or 2 things to talk about. What is a real world question that could combine all of this together? We actually, kind of took a look at our customers, our verticals, and one that kind of brings it all together would be this question, which is find anyone who works at VMware and knows each other directly, where there's a relationship, and whose name sounds like Jacque or Ivan, so isn't spelled like it, but sounds like it. I'd like them to have withdrawn an amount of about $200 or more within 24 hours, within the last 24 hours, at some ATM, some cash machine, less than 2 kilometers from this X and Y, this latitude and longitude. This is a real world question that if you were a bank or if you were maybe a gas station that had ATMs that you'd be very interested in so that you could cross-sell, upsell, and better provide services to your customers. And so an example function for something like this would be like this, and you're looking at approximately 30 lines of quote unquote code. where we're using a text analytical search function to find people that work at VMware. We're using a Apache Madlib breadth first search engine function to see if there's some kind of direct or indirect link between those people. We're using the built-in SoundX function to see if the names actually sound like Jacque or Ivan, with standard SQL for greater than $200, with standard PostgreSQL for time functions within 24 hours, and then standard PostGIS functions for that lat and longitude. And so the ability to combine Postgres and Greenplum with lots of data, allows for these real world solutions. And if you're to look at an alternative way of doing this without Greenplum,
and Jacque, one thing before you move on from that, if you go back, there's one more thing you're using here, which is you're using procedural language, using PL/PG/SQL, which gives you for loops and variables. So you've used Postgres PL/PG/SQL to orchestrate all that and create a loop, and then do all those things you said.
Fair. So we took a look at what it would take to do in a typical, kind of non-Greenplum environment. In this case, this would be like the Hadoop ecosystem. In the Hadoop ecosystem, first we need to load the data, into HDFS and into Hive. We need to index it and search it. We'd write some code and maybe pull it into a Spark data frame. We would continue on and do some Solr linking and maybe some graph analysis, do a little bit more distance calculations. At the end of the day, we've been moving the data back and forth between different platforms, if you will, as part of the ecosystem. And we've taken what was 30 lines of code inside of Greenplum and made it effectively 3,000 lines of code in Hadoop. The beauty here is that with Greenplum, you got one query using all of these built-in functions, one platform, no data movement, and you can really answer these real-world
and
questions.
Speaking of going back, Jacque, speaking of massively parallel in a sense, right? If the average developer can write 100 lines of production code a day, you're talking about 30 working days of development to write this in Hadoop, and you're talking about 3 hours to write this in Greenplum.
Right. And so again, you kind of look at the, this Greenplum ecosystem here, where you've got the ability to move data within the ecosystem, connect to any kind of storage platform, deploy to any, infrastructure, do data science, business intelligence, machine learning, and even the HTAP, hybrid transactional analytical processing that we were talking about before. You truly have this one-stop shop for any kind of analytical queries that you might want to do at any scale, and know that all of this data science, all of that SQL, all of the tools that you're using to connect to and interact with Greenplum are completely compatible with Postgres, which makes it that much easier for your developers to deal with two bespoke different, I won't say platforms, but two bespoke different use cases, transaction versus analytical.
Right, with an Apache license, which gives people the right to use it for free.
Exactly. So, Ivan, I know you took some time out today. You were at VMware Explorer.
Yeah. We renamed VMworld to VMware Explorer. I'm there today. If you want to see our booth, we have our customer Dell Technologies there at VMware Explorer showing how they run 8 million queries a day on Greenplum to run their supply chain and marketing analysis for their $100 billion company. So stop by the booth and have a look. Also, they also, as we say, Greenplum runs on any hardware. They're running it on their Dell PowerFlex storage, which gives optimal software bit-defined storage to scale out to petabytes. So have a stop by us in San Francisco.
And if you're not in San Francisco and you want to just scale to new heights, you can learn more at greenplum.org. You can learn a lot more on the YouTube channel for the Greenplum database. And both Ivan and I are always available for chats and deep dives. So please reach out to us.
And thanks to the Postgres TV team for having an awesome channel on YouTube that has all this.
Thank you for coming. Thank you.
Postgres technology. Yeah.
I actually, if you have a couple of more minutes, I
Sure.
wanted
Of
to ask
course.
a few questions. First, I'm fully Oltp guy, so I ask questions like if you obviously make some moves towards Oltp, okay, HTAP, and thinking about like okay, various types of indexes. You're adding BG bouncer, which also looks like this area, right? But it's always there is always this, you call it master node, like proxy, which is also like also a database, right? Like Postgres
Yes.
or
Yes.
right. I'm interested to like have you like what are the numbers of latency overhead of having this intermediate
Yes.
Postgres?
So okay. So first of all, again, we're by no means making an intention to design a system optimized for pure OLTP. The journey was having built an Olap analytical database on Postgres that the real world users told us that Olap databases need to have OLTP functionality, right? Integrated. So they're not expecting the level of OLTP you get in a pure OLTP solution, but they absolutely need basic OLTP functions, right? So the scalability of the OLTP doesn't need to be 10 times faster than Postgres, but ideally it should be as fast as one Postgres. And there is, as you said, extra latency added. So a single Postgres will be faster at OLTP than Greenplum at doing transactions because it doesn't need to make those extra hops, right? But we can do 100,000 transactions a second in optimized environment. We can do, 30, 40, 50 millisecond latency queries. But in a single Postgres, I'm guessing you could probably do 10 millisecond, or you can do 500,000 transactions. You can certainly get, let's say 5 times faster in a Postgres system. But when you compare it, for example, to something, and I don't think I'm speaking out of turn to say something like an Amazon Redshift or a Snowflake, how many transactions per second of updates and deletes can you do in those databases? And I think the answer is somewhere between 0 and 0, right? There's literally don't even have the concept of
not supported.
Don't even have the concept of a transaction, right? So, or if they do, maybe the answer is you can do 2 per second. But when you say, hey, we can do 100,000, now you've got a data warehouse, right? That can run. And why do you need a connection pooler? Well, what if your company has 5,000 analysts, right? That the connection pooler helps, right? So really,
or you expose some interfaces to your clients and not only inside the company.
So it's not, we don't introduce HTAP to say we're the best at everything. We introduce HTAP to say we're the best at analytics. Because we learned that from users, that an analytics system must have OLTP functionality and high concurrency.
Makes sense. And one more question also from this. Well, actually, I want to say thank you here because your slide about explaining what exactly you take from OLTP world to make it more like HTAP, it helped me to understand it better because usually I thought only about latency overhead, and criticized all systems because of that. But you say we need updates, we need indexes, makes sense. Concurrency makes sense a lot. Another question, we discussed ability to store some data on S3 or object storage. I think in the case of GCP, it will be, they call it GCS. On Azure, it will be blob storage, or doesn't matter, right? But I'm very curious in terms of HA and DR, because compare S3 compared to EBS volume, they have different characteristics in terms of availability and the reliability of storage. And for example, it's quite it can happen that S3 is down, EBS volume is up, S3 is down. What happens with Greenplum if this case occurs?
Yeah, we would not put data in S3 that had a availability requirement better than S3's availability offer, right? So when you pick S3 as a storage, you have to understand that S3 has this amount of availability. If you try and query it, you're going to get an error if it's down.
Or write to it. Okay, but so I understand this, but still, like if I made decision, it's already there. What happens technically with Greenplum if S3 like unavailable? Whole node is unavailable, or you have concept of partial downtime or something?
No. So again, if you have a data in S3, what'll happen is you'll write a query. The query will get optimized to a query plan. At the bottom of the query plan, you'll have an external S3 scan node. When the external S3 scan node runs, it'll get an error, and the query will come back with an error saying can't access the data.
Right.
Which is what you would actually want if you're substitute S3 for a hard drive. If your hard drive was broken, and not all of your hard drives were broken, but just one of them, you wouldn't want to return the query because you wouldn't have all the results.
That being said, we have a kind of a dividing line between managed storage and unmanaged. So managed storage means that it's processed through the traditional Postgres internal table structures. External storage, it's like a foreign data wrapper. So if it's an internal storage, we replicate 2 copies. Right. So we will have, if we're managing the data, like S3, we can't control. Someone could come in and do whatever they want. Right. Mm-hmm. But for managed data, like when we store it on the hard drive or whatnot, then we will have 2 copies. We'll have a copy on machine 1 and a copy on machine 2. And if machine 1's down, we can serve it from machine 2. But for external data, there's a lower availability guarantee. Right, you have to wait for that to become available before you can access it because we're not managing that. So there's managed data, which is internal to Greenplum, like in Postgres files in the same directory structures. If you do ls and look at the files, it'll look like Postgres. That's managed data, and we replicate that using wall streaming. But if it's in HDFS or S3 or Oracle, then it's just a reference. It's not actually managed by us.
Like foreign table.
It's a foreign table, and it will only function if that foreign data source functions.
Makes sense. And what's your advice to those who have, for example, quite big installation of Postgres, which is growing like say 10 terabytes, right? And there is also obvious need to have analytical something because running aggregates in Postgres becoming worse and worse, right? What's your advice? How to start with Greenplum having Postgres?
Right. So we have, I'm thinking of certain customers like who started with single node, right? So if you have Postgres, and you have 10 terabytes, the first thing you might look into is just running single node Greenplum and have like 8 Postgreses on one node. We have some financial customers that did that for years because it gave them better performance for their analytics than one Postgres. And then 5 years down the road, they said, well, let's talk about clustering. Let's run 4, 8, or 16 nodes, right? But for the first 5 years, they were just good running single node Greenplum with like 10 Postgres seconds.
Yeah, and I'll throw in there, not to reference a Happy Gilmore movie, but Greenplum eats 10 terabytes for breakfast, right? 10 terabytes is relatively small for what we're capable of. And put another way, you could imagine a scenario where you could put a Greenplum and leverage foreign data wrappers with Postgres and just experiment like what's slow inside of Postgres versus what's fast inside of Greenplum. We've also seen customers put something like PG Pool in front of Postgres and Greenplum and then route queries from one to the other depending on what they are, transactional or analytical. And now you're making an open source based, essentially Oracle Exadata, where you can literally have queries routed to, to take advantage of whether they're Oltp or Olap. And that's all seamless again to your application.
There's a paper that was published on that from a shipping company on the internet. If you search for shipping Postgres Greenplum something, they basically had 2 Postgreses, one for their OLTP shipping data and one for their historical shipping data. And then they had a geospatial app that would basically call the Postgres port for the this kind of stuff. And then when it wanted to show the graphs of historical data, it would call the the Greenplum port and show where are all the ships and all that, right? So there's I think it was called Exact Earth. If you search Exact Earth, Postgres, Greenplum, there was an article out there on the internet about that.
Yeah, I will try to find it and add the link. But what if I have Postgres, I have Greenplum? What's the best way to connect them? Maybe like to have some CDC or something. Like, is it through Kafka or?
You can do CDC into Kafka and then load those rows into Greenplum. And
but should I use like things like Debezium or something else? Like what should I use?
You can use
What's
that
the best? What's the best?
The one you mentioned, I forgot the name, Debezium. I have heard people like that. That's a free version, right? And then there's all kinds of
open source.
Debezium.
What I would throw out there though is kind of what we were talking about, right before the call. It's a consultative answer, but the best actually depends upon the organization, right? The use cases, the talent that they have, etc. So like your usage, like some of our customers, they only know Informatica. And so entering in something else besides Informatica might be super difficult for them. Whereas for you, Informatica would be a big overhead, for example.
But Debezium, I have seen people work with and has good reviews, right? So you could do Debezium and then generate the data.
Mm-hmm. Okay, thank you. No more questions from me. Ilya, you do have any, or let's call it. Oh, you went
muted. Reverse.
Yeah,
you just muted.
Sorry. Yeah, I just muted myself. No, actually, it was quite comprehensive, and I think lots of technical details we heard of how Greenplum works. So basically, thank you guys for coming and for explaining a lot of things and coping with us with our technical problems as well.
Yeah, apologies once again.
The moral of the story is that if the moral of the story is if you love Postgres and you want to and you like open source, and now you have a data warehousing problem, don't go to a non-Postgres proprietary solution for your data warehousing, right? Go to an open source Postgres solution for data warehousing. Don't go to the dark side.
Yeah,
right.
And you will have a choice. Yeah.
Yeah, exactly.
Right.
Yeah, great.
Great, thank you so much. I encourage everyone, as usual, to like, subscribe, share, especially share in all social networks and working groups where we discuss databases. Thank you so much, guys.
Thanks, guys.
See you later.
Thanks, guys.
Bye-bye.
Yeah, appreciate it.
Yeah, thank you, and have a good day.